For this question, we're being asked to draw the Lewis structure for xenon dichloride, and there are a couple questions that we will need to answer using this structure. So first, let's identify the central atom for xenon dichloride and also figure out how many valence electrons do we have to work with. So our central atom is going to be xenon because it is less electronegative compared to the chlorines. And we have 8 electrons coming from xenon, and we have 7 electrons from each of the chlorines, and there are 2 chlorines, so we get a total of 22 electrons for our valence electrons. And using that, we can come up with a structure like this. So we have a full octet for chlorine and a full octet for the other chlorine, and whatever electrons that are remaining, so 22 minus 16, we get 22 minus 16, we get 6. So that means we have 6 lone pair electrons surrounding our xenon, and 6 divided by 2 is 3, so we have 3 lone pairs. So let's start answering a couple of the questions we have. So how many electrons, valence electrons, are present in this compound? We already answered that here. There are 22. And how many bonding electrons are present in this compound? There are 2 bonds made to the chlorines by the xenon, so there are 4 electrons here because there are 2 electrons in each of these bonds. So there are 4 electrons, 4 bonding electrons. And how many lone pair non-bonding electrons are present in this compound? So any electrons that aren't being used in a bond are going to be lone pair electrons. We can either count up the number of electrons, or we can simply subtract 4 from 22 and we get 18. So moving on, we're given a couple of structural representations of xenon dichloride, or we're being asked if there's anything wrong with them, and if there is something wrong with them, to say what is it that is wrong about them. So a reminder of the structure that we have from the previous slide, here it is on the bottom left corner. So let's start by looking at the left structural representation. So here we have all the lone pairs on the equatorial axis, and we have all our chlorines in the axial positions. So seeing that, we do have 3 lone pairs according to our drawing that surround xenon, and our chlorines are in the axial positions, which maximizes the electron densities away from each other. So this would be a pretty accurate representation, which incorporates VSEPR theory for our xenon dichloride. So we say there's nothing wrong with this representation. So let's take a look at the middle one. So we have 2 chlorines in the axial in the equatorial positions, along with 2 bonding two lone pairs in the equatorial positions as well. But we also have 2 lone pairs in the axial positions. So because we said previously there are only 3 lone pairs that surround xenon, there are way too many lone pairs that are surrounding xenon in this representation. So this is wrong. This is not the correct representation because there are too many electrons that surround the central atom. So finally, let's take a look at the structure on the right. So xenon is bonded to 2 chlorines, which are both in the equatorial positions, but they are about 120 degrees away from each other. And we have 2 lone pairs that are in the axial position that are 180 degrees away from each other. So according to VSEPR, we want to maximize the electron densities distance as best as we can. However, what would take priority would be the chlorine atoms. So we want to maximize those first. So because it could technically be in a 180-degree bond angle from each other, but instead we are in a 120, we are not doing that to our best capability in the structure, representing that to our best capability in the structure. So they're actually, this representation is wrong because the electrons are in the wrong locations according to VSEPR. So finally, what are the approximate bond angles made by the atoms of the structure? So taking this to be the most accurate representation of our structure, the two chlorines are about 180 degrees away from each other. So what is the shape of xenon dichloride? So if both these chlorines are about 180 degrees away from each other, this kind of looks like a line, right? So this would be linear. Next question asks, what is the geometry of xenon dichloride? So because xenon dichloride also contains 3 lone pairs that surround the xenon central atom, xenon is actually bonded to 5 different electron groups here. 3 lone pairs and 2 chlorine atoms. So because it's bonded to 5 different groups, we can think this would take on a trigonal bipyramidal geometry. Finally, is xenon dichloride a polar or nonpolar compound? So in order to answer this question, we have to take a look at the dipole moments. So because xenon is bonded to a chlorine atom here and a chlorine atom here, and xenon is less electronegative, we can draw our dipole moment arrows like this. So xenon will have a partially positive charge, and our chlorine atoms will have a partially negative charge. So we can also draw one right here like this. So because of this, we have 2 arrows of the same magnitude pointing in different directions. So because of this, they cancel each other out. So this makes xenon dichloride a non-polar compound.